And welcome back, students, to our introduction to the LC3. We're going to continue talking about circuits and gates. So we're going to kind of pick up where we left off last time with talking about logic gates. So if you recall, the logic gates and or not, their behavior is dictated by the switch behavior of MOS transistors, or metal oxide semiconductors. Now, there also exist CMOS circuits, or complementary MOS, and these use both N-type and P-type MOS transistors. Typically what you'll see here with these is that P-type is attached to a positive voltage and pulls the output voltage up when input is 0, and N-type, which is attached to GD and pulls the output down when the input is 1. So positive up, negative down. Here's those basic logic gates again that we're kind of familiar with: our NOT, our OR, our AND, our NOR, and our NAND. And you can see that if you're familiar, so you can see that some of the output language is a little different in this diagram. Like in this diagram, you can see that OR is A plus B, AND is AB. NOT has a horizontal line over the top of A, and you can see that horizontal line also exists over NOR and NAND, because if you recall, a NOR is a NOT of an OR gate, and a NAND is a NOT of an AND gate. Now, we can't talk about anything else without first talking about De Morgan's Law. And what De Morgan's Law talks about is how we convert from AND to OR with a little bit of help from our NOT gate. And so if we look at the following logic gate, right, you can see we have an A and B, and then they're being inputted in. You can see the little circle there for the inverter gate, and then there's a circle at the end. And what this means is that in order to convert from AND to or really technically vice versa, we're going to invert the inputs and then outputs. So we're going to start first with our AB. So AB, it's 0, 0, 1, 1, and B is 0, 1, 0, 1. Our typical kind of configuration that we see with logic gate. Then, of course, we invert them. So that's invert of A, invert of B. And so A is now 1, 1, 0, 0, and B is now 1, 0, 1, 0. All right, so all we did was we flipped each of those states. All right, then, of course, we did the AND operation of those two. So, well, the AND of 1 and 1 is 1. The AND of 1 is 0 is 0. And then the 0 of 1 is 0. And 0 of 0 is 0. Then we take the AND of that whole thing that we just did, and we get 0, 1, 1, 1. Now, if you look, this right here is an OR gate. All right, this is an AND gate, which is what we're used to seeing. So this right here kind of started us off. We're like, hey, we're going to take it and flip these to get our AND, and then we went and made our OR gate. Because you remember, the only time that you get a true in an AND gate is if both the conditions are true, and the only time you get a false in an OR gate is if both conditions are false. So really, AND and OR are kind of like the opposites of each other. All right, and that's what this is applying down here. It's the same as A plus B not. All right, same as A plus B, which of course, if you recall back on our previous slide, A plus B is our OR gate. All right, so that's how you get from AND to OR. And you might be wondering, well, why do I need to know how to get from AND to OR when I could just do an OR gate? If you remember, the LC3 only takes 3 kinds of logic operators. It'll do AND, it'll do ADD, and it'll do NOT. So in order for us to get an OR gate, we're going to have to be able to use NOT, ODD, an AND gate. Now, what's if you have more than 2 inputs? Right? Because almost everything that we've looked at in this course up to now, you had 2 inputs. You had A and you had B. But what if you have like A, B, C? Well, the good thing is AND and OR can take any number of inputs. There's not a limit. So, and we kind of know that if we have a 0 at endpoint, it's false. So in order for it to be true, we just know, well, if it's an AND gate, if all of the inputs are 1 or true, then the answer has to be true. Similarly with OR, if I have a 1 in any of the inputs, I know the answer is 1. And of course, similar things happen with AND and OR, because they're just flips. And of course, that's kind of what this diagram is illustrating here. So you can implement this with multiple 2-input gates, or even a single CMOS circuit. Now, we also need to talk quickly about a decoder. And with a decoder, you have n number of inputs, And what that means, there's 2 to the n outputs. So this means that exactly one output is one for each possible input pattern. So let's look at this diagram here because it might make a little more sense. So in this diagram, you can see I have A and B. So I have 2 inputs. So if I follow that rule, it should be 2 to the power of n, or in this case, 2 to the power of 2. So we have a 2-bit decoder. That means that there should be a total possible outcome of 4 outputs. Now, what's if I had 3 inputs? How many possible outputs would I have? Well, if I had 3, well, let's do the math. 2 to the power of 3 is 8. That means I have 8 possible inputs. If I had 4, I would have 16, etc., etc. Now, next we need to talk about a multiplexer, or a mux. Now, this is kind of the opposite of what we saw with the decoder page. We have an n-bit selector and 2 to the n inputs and only 1 output. So the output equals one of the inputs depending upon the selector. So you can see here S1, S1 and S of 0, and you're going to run it through the program. And you have 4 inputs, A, B, C, D. So you get output A if S is 0, 0. You have B if S is 0, 1. C if S is 1, 0. And D if S is 1, 1. So like I said, this is kind of the opposite of a decoder. And if you don't understand exactly how a multiplexer works right now, or a mux, that's okay. I'm not going to necessarily, you don't know exactly everything about how a mux works, but you should know what a multiplexer is and kind of what it's doing. It's taking multiple inputs and processing it to generate one output. Now, we also need to talk about logical completeness. In logical completeness, you can implement any truth table with an and, or, and a not. So in this, we have and combinations that yield a 1 in the truth table. So if we look here, I have ABC again, right? And obviously, I'm going to start off first saying everything is 0. So I know then the output has to be 0 because we just know by that combination, it's got to be 0. Right? Then we're going to OR the results of the AND gate. So we start here. We got I do the next row. Okay, well, we got 0, 0, 1. Well, that's 0. Then I got 0, 1, 0. But you notice that time, I have a 1. Here, I have 0, 1, 1, and a 0. Then I have 1, 0, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, and 1, 1, 1, 0. Again, you might be wondering, how does this work? Now, this one is pretty easy to understand. You have all zeros, you have a 0. But you might be wondering, well, why do I have 3 1s and I get a 0? Again, if you look at this, it says and combination that yield a 1 in the truth table and OR the results of the AND gate. So if you follow our flow in here, you can see how this works. You have some inverters in place here. So you have A and it's going into both these. So you have A going here, and you also have C going here. Then you have B going here, and B here. And you can notice that these are knotted. Right? So in this first gate here, really, if you were to look at this table in its full might, you would have a A, which is not A B, and a C. And then over here, it would be a similar thing. Once those process through those gates, you're going to have an OR here, and then you have a D here. Again, this is not something I'm going to have you stress too much about right now, but this is just more for your information. But what you do need to know, though, is memory. And memory is a logical K times M array of stored bits. So you have the address space, which is the number of locations, usually a power 2. Makes sense, because everything is binary. So you have K to the power N locations. And then you also have addressability, which is the number of bits per location, so byte addressable. And it's M there. Now, of course, this is not the actual way memory is implemented. There's fewer transistors, it's much more dense, and relies on electrical properties. So this is kind of just like a basic, like, hey, here's memory. It's a little bit more complicated than that. But the logical structure of how this is done is very similar. So there's address decoders, you got word select line, word write enable, and then there's of course two basic kinds of RAM. You have random access memory, which is broken down into two categories. You have static RAM, SRAM, which is fast, maintains data as long as power is applied, and dynamic RAM or DRAM, which is slower, but denser, bit storage decays, and must be periodically refreshed. Now next, let's talk about combinational versus sequential. There are two types of quote-unquote combination locks here. Right? The first one, of course, is a combination, the second one is sequential. In a combinational sequence, the success depends only upon the values, not upon the order in which they're set. So if you look at this kind of lock here, all you need to do is have your numbers line up and you can open the lock. It doesn't matter which way you turn it. It doesn't matter if you do lock 1 first, lock 2, you just have to line them up. With the sequential lock, success depends not just upon the numbers, but upon the sequence of how you do it. So, for example, right 13, left 22, right 3, then the lock will open. The other lock doesn't have a differentiation between right and left. All it wants is the numbers to line up. And this is very important when you start looking at things like, for example, privacy and security issues and stuff like that, because you want your numbers not just to match, you want it to be in a certain sequence. Let's talk a little bit more, though, about combinational versus sequential. In a combinational circuit, this is always going to give the same output for a given number of inputs. For example, an adder, an adding circuit, always generates a sum and then a carry, regardless of previous inputs. A sequential circuit stores information, right? And then that output depends upon that stored information or state plus whatever the input is. So a given input might produce different outputs depending upon the stored information. A quick example, a ticket counter. Advances when you push the button, and the output is going to depend upon the previous state of the button. So, button time might be 12, and then next one comes through, it's 13, then 14, and so on and so forth. This is very useful when you're building memory elements and state machines. Speaking of state machines, it's another type of sequential circuit. This combines combinational logic, so some of that combination stuff we just talked about, with storage. So it will remember, quote unquote, a state, and then changes the output and therefore the state based upon inputs in the current state. So if we look at our state machine here, you have some input coming in, it runs through the computational logic circuit, goes through any storage elements it needs to do. So for example, if you look at programming language, it's updating variables, stuff like that, and then it's going out through an output. Of course, I should probably define also what a state is, because I'm using this term a lot. Well, when we're talking about state, we're talking about the state of a system is a snapshot of all the relevant elements of the system at the moment when the snapshot is taken. So the example I gave earlier was variables. If you're taking a value of something, or string, or some other primitive object type. That's just a quick example of something that is, if you were to look at the value of something at a given moment in time, that is a state. And if you look at that like 2 minutes later and see what the values, and if those values have changed, that's now a new state. So some quick examples. The state of a basketball game can be represented by the scoreboard. You have things like number of points, time remaining, who has possession of the ball, etc. All those things are different states. If I look at number of points, that one's pretty self-explanatory. You start scoring points and change the point value. How much time remaining? That's very important to know when the game's going to end. And possession, who has possession of the ball? So it's either Team A or Team B. Additionally, things like the state of tic-tac-toe board can be represented by the placement of X and O's on the board. Is it in possession by an X? Is it in possession by an O? Or does nobody possess that square right now? Now, let's talk then, now we know what states are, but the state of a sequential lock. So our lock, let's say in this example, has 4 different states, labeled A through D. So this is like a, if you really want to think about it, a 2-bit example. And in this one, we have 4 states. State A, the lock is not open, and no relevant operations have been performed. So pretty much the lock is sitting there. Nobody's touched it. State B, the lock is not open, and the user has completed the write 13 operation. Notice they did the first spin. State C, the lock is not open still, but the user has completed write 13 followed by left 22. And the last one, state D, the lock is open because remember they had to go write 3, and that would open the lock. So that is the states of a sequential lock. After the lock is open, then of course you could shut it and it's going back to state A. Now, let's talk then about finite state machines, because finite meaning that there's not an infinite number of states. So this is a description of a system with the following components. So in a finite state machine, you have a finite number of states. So if we look at the previous page, 4. It has a finite number of external inputs and a finite number of external outputs. If we think about it, we had kind of like different. So if you think about that lock, there's only so many different inputs of numbers that you can have on it. And then of course the outputs, it's either lock open or lock shut. There's an explicit specification of all state transitions, and an explicit specification of what determines each external output value. So in order for the lock to open, it had to have write 13, left 22, and write 3. Now this is often described by a state diagram. I'm not going to put a state diagram up here. It's just an illustration that shows how, as you move through the different states, how the machine would change. Now, of course, this often triggers state transitions, so by the inputs, and outputs are associated typically with each state or each transition. So as you're moving from closed to open, what was the output that was associated with that? Now, let's look at the finite state machine. In this one, you could have, for example, a clock example of up and down. So combinational logic, again, determines outputs in next state. There are storage elements here which maintain state representation. So you can see it's very, very similar to what we saw previously. The only difference is that this is now just we're applying something to it. So in this case, a clock. All right, let's go from logic to a data path. So the data path of a computer is all the logic used to process information. All right, we're going to look at that data path for the LC3 on the next slide. And it's going to look very complicated. Don't worry about it and don't get overwhelmed by it. There's combinational logic, which include things like decoders, which converts instructions into control signals, multiplexers, which select inputs and outputs, ALUs, which are the arithmetic and logic units, which are the operations on the data. They're pretty much the calculators for the machine. And then you also have sequential logic. You have the state machine, which coordinate control signals and data movement. So it's like, hey, this output's been done, the input's been done, and there's the output. What's the next state to do? And then you have registers and latches, which are your storage elements. So if we look at the LC3, you can see we have several combinational paths. So right here, you have a mux right here. You also have in here, there's some more. You can see right in here some more muxes going on in here. Looks like some additive ones. Then down here you have an ALU. So that's your arithmetic and logical unit. Storage, you can see you have a registry file up here. And down here you have an IR. And then of course you have your finite state machine right here. And of course all this is going across this big bridge here as this computer moves through its different processes. Again, don't worry too much about what the data path looks like. What do all these different values mean? We'll start looking at some of these things as we get into things. But I want you to start knowing some of these terminologies so that way when we start talking about them, we start using them for the LC3, you're not totally lost and confused. And that concludes our notes, folks. Until next time.